Okay, so we're going to kind of go through this relatively quickly. Let's take a look at acids and bases. There's a lot of like nuance in here, and there's a lot of conversations to have a little bit more deeply, but frankly, we don't need to worry about that. So I'm just going to kind of give the important stuff. So first of all, let's talk about acids and bases. There's a couple of things we're going to talk about. You're going to hear a lot of these terms. The hydronium ion. This sounds super fancy. But before we start with that, H plus. H plus, which is basically just a proton, but the H plus aqueous is what we primarily look at for acids. So what you might hear for H plus is me refer to it as a proton because it's essentially a hydrogen, which is one proton and one electron, without the electron, making it just a proton. So a proton, an H plus, that's pretty much it. Hydronium, the hydronium is an H plus added to water. So H3O plus aqueous, this would count as a hydronium ion, right? We don't use this. This is the more proper way to look at it, but H plus is kind of the shortcut. So H3O plus is basically, okay, I take this H plus aqueous and I combine it together with a water molecule, which is liquid, and that creates H3O plus aqueous. Okay, so you kind of get those things together. That's where it comes from. This is more proper to talk about it as a hydronium ion. It's a water molecule that replaces one of those pairs of electrons with, and this whole thing is positively charged. This is again, the more proper way to look at an H plus in aqueous solution, but we don't typically use that. We typically say H plus. It's just kind of how we do it. The next thing is for bases, H minus, OH minus, which is hydroxide. And that's really the only way to refer to it. Hydroxide, again, also aqueous. So this is typically bases. This is typically acids, but they kind of work together because when I combine an H plus with an OH minus, I am going to get water out. So they kind of come together to form water. And in fact, even if I looked at the H3O plus OH minus, I end up with two water molecules. So either way, typically what we see is the hydronium represents that's what we use for hydronium most of the time, but H plus is acidic and hydroxide OH minus is basic. So we're going to use these two things together, but together they neutralize one another as acid and a base neutralize one another to give me water. Okay. So what is an acid and what is a base? So an acid produces piercing pain. Yeah, it's really painful to get covered with an acid. And it tastes very sour, like the examples down there, oranges, lemons. So any citrus has that citric acid in it. Vinegar has acetic acid, so you get that kind of that flavor, that very sharp flavor. So it's acid, it's how it responds. They have a pH less than 7. 7 is the neutral pH. Anything below that is considered acidic. Bases, on the other hand, they're typically used for cleaners like soap. Get that slippery feel whenever you pick up like a bleach or a cleaning agent. It feels very slippery. That's because they're bases. Okay, they taste very bitter. So I don't think you've ever bitten into soap, but certainly if you have, you're going to notice that it's bitter. So there's a bitterness involved with those. And their pHs are greater than 7. Okay, so greater than 7, greater than 7, just so we're sure of and less than 7. Okay, so those are acids and bases, H plus and OH minus. And let's talk about defining these things. So the definition of an acid, and there are 3 definitions that we're interested in only 2 of them, but acids and bases have a number of different definitions. We have to define them as chemists and say, well, what is going on at the molecular level to make an acid and a base a base? So Arrhenius, a Swedish chemist in 1884, was the first one to define an acid and a base. he defined an acid as something, any substance that increases the H plus in aqueous solution. So if I drop an HCl, which we know is an acid, into solution, so we're going to combine it together with some water, you end up with H3O plus aqueous, and what's left over is the chloride aqueous. And I want to point out that H3O plus is just simply H plus. So it is producing H plus in solution. Okay, so anything that increases the H plus in solution. Yeah, so let me just say the simple way of saying that, and that's why we use H plus, is HCl becomes H plus aqueous plus Cl minus aqueous. So that is anything that increases H plus in solution. How do you identify an acid? And that's going to be kind of important. Identify an acid. This is a quick aside. Acid. You're going to see you're going to see H first. So anytime you see a hydrogen first, you're going to say that thing is an acid. Okay. And the other thing is you're going to identify the group on an organic. You typically see this COOH if you see that at the end, or CO2H. Both of those are considered acids. Okay, so for us, it's going to be H first. Anytime you see H first, you say, that thing's an acid, and there we go. In terms of base, a base is any substance that increases the concentration of OH minus in solution. So NaOH, if I drop that in solution, which is a solid, if I drop that in solution, I end up with Na plus aqueous, which I don't really care about, but I do care that it actually puts aqueous OH minus in solution. That is identifying a base. How do I identify a base? Just we're looking for that. Identify a base. For you guys, all you really have to worry about is looking for OH minus. Is OH minus present? Yeah, if OH minus is present, then you have a base. If you want to get a little more advanced, I'm looking for some nitrogen group. Anytime you have NH3 in an organic, or NH2, or NH something, or NH, or N, any of those will count as bases. But we're really going to focus on the OH minus. We're just looking for OH minus. I'm not going to use any fancy bases on you. Okay, good. So H plus in solution or OH minus in solution. But the important part here is it's aqueous solution. So his definition is limited to aqueous only. So anything in water, okay, which we're limiting ourselves to. We did nomenclature already, talking about there's two types of acids. There's a binary acid, which is just two substances together, like hydrogen plus an element. So HCl, H2S. And simply, you're going to take the hydro, you're going to take the root and ic acid. Hydro, root, ic acid. So in this case, it is hydrochloric and hydrosulfic or sulfuric acid. That's how you would name those two. Binary acid, element with hydrogen. The next is oxo acids, which are basically, I didn't call them oxo acids, I just simply called them acids made from polyatomics. Again, you take the root and you end with ic acid or us acid. So, and this is my mnemonic for this is any polyatomic ends with 8 goes to ic, and ite goes to ous. Adic itis. Again, it sounds like a disease. Adic itis. But of course, you have to add acid afterwards. So I know that SO4 is sulfate. 8 turns into ic acid, sulfuric acid, and you'd be fine. Sulfic acid would be fine too, but sulfuric is typically what we call it. HSO3, SO3 is sulfite. The ite returns into OUS acid. So sulfurous acid. Okay, so again, 8 goes to ic, ite goes to us, adic itis. Okay, good. With that naming done, let's talk about the next definition. So the first definition was Arrhenius, producing H plus or producing OH minus. Very discrete, right? Produces H plus, it's an acid, produces OH minus, it's a base. Bronsted-Lowry, and this is the one we would use more often. Bronsted and Lowry in 1923, so this is like 40 years later or something, or 30 years later, he defined an acid as a proton donor and a base as a proton acceptor. So we're going to use the same acids and bases that we did before. So if I have HCl, aqueous, plus water, liquid, we end up with H3O plus aqueous and Cl minus aqueous. So if we look what happened, HCl turned into Cl minus. So it lost H plus. Or what we could say is it actually donated H plus to the other part of this, which is water. And in this case, water became H3O plus. It accepted H plus, or it got an H plus, right? So lost H plus and then accepted H plus. So in this case, because HCl donated the H plus, we would define this as the acid. It donated it. And then base is a proton acceptor, H2O in this case, and I probably should just move this down below, and I'll do that. H2O in this case accepted, and therefore it counts as the base. Okay, so again, proton donor is the acid, proton acceptor is the base. So we call these pairs a conjugate acid-base pair. In this example down here, H2O becomes OH minus. Okay, so it's the same kind of setup. And in fact, let me just write this on our own, and then I'll scroll back up. So NH3 plus H2O yields NH4 plus aqueous plus OH minus aqueous. So in this case, NH3 goes to the other nitrogen compound, and water goes from it to the OH minus. So what we notice is this goes from NH3 to NH4 plus, so it gained, so plus H plus, so gained, or I should say not gained, but accepted. So before we continue, if it accepted the H plus, it is going to be considered the base, where water is going to lose, or so minus H plus, it donated it. Donated that H plus, and this is going to count as the acid. Again, base, acid, accepted, donate. So we call these things, so these two right here, the water and the OH minus, those are called a conjugate acid-base pair. So in the other direction, and we're going to kind of skip this, but OH minus going back in this direction, it would be the opposite. So if it's an acid in this direction, it's a base in the other. So we call these a conjugate. We call these a conjugate acid-base pair, right? So we just pair them up. HCl and Cl minus, it's an acid and base conjugate. H2O, H3O, it's a base and it's acid conjugate. Okay. All right. Good. So moving on, we need to talk about strong and weak acids and bases. So we talked about strong electrolytes. These strong electrolytes are going to be the soluble ionic compounds. Again, it's anything on the solubility table that's aqueous counts as a strong electrolyte. These strong acids, there is a collection of 7 strong acids. And if you look at your periodic table, it's going to make a little bit more sense. So HCl, HBr, HI. Okay, those are all considered strong acids. Next to HCl is sulfur. So H2SO4 and HNO3. What you're going to notice is missing is oxygen and fluorine. So I'm focusing on the periodic table, nitrogen, sulfur, chlorine, bromine, iodine. So those right there, all around fluorine. HF is not a strong acid, okay? So nitrogen, sulfur, chlorine, bromine, iodine. So that little ladder right there is the strong acids. I'm going to add two more to the chlorines, HClO3 and HClO4. Those are the other two. Again, these are just chlorines. These are the other two strong acids. So that collection right there is the list of strong acids. They donate hydrogens, okay? So with that said, what is considered a weak electrolyte? Again, weak electrolytes are insoluble. Okay, so the things that form solids in solution. So go back to your solubility table. What are considered weak acids? Any acid that is not strong. So anything that's not on this list above is considered weak. So HF, weak. H2S, weak, because it's not in that list. HClO, weak, because it's not HCl3 or 4. Okay. How about C2, let's see, CH3COOH. And that's the other part of this. We kind of want to look out for that group right there. This is an organic acid. We see these in citric acid. This is actually acetic acid for vinegar. So anytime you see COOH, that's the list. So anything that is not strong is considered weak. Look out for the COOH, or the other way of looking at that, CH3CO2H. They rarely do it this way, but that is also the same thing as above. We just combine the oxygens together. Okay, both of those, all of those are strong. So weak acid, strong acid. Okay, good. Notice that I did not put weak acid. I did not put bases here. The strong bases are the soluble hydroxides. Yeah, so I guess let me briefly talk about that. So the strong bases are the soluble OH minus compounds. So basically you would already calculate those strong ones based on looking at the solubility table. So that's kind of why I don't talk about them. But I can just simply tell you group 1 and hydroxide. So something like NaOH, lithium hydroxide, etc., and the heavy group 2s, NOH. So calcium, strontium, and barium. That's the list of strong bases. Okay. But again, it's the soluble hydroxides. You don't have to look. And any hydroxide that is not on the solid is basically a solid is going to be considered weak. So all of those are included in the solubility table. Acids are the only weird ones where we have to kind of look out for them. Okay, good. Next up, the autoionization of water. This is a really kind of strange concept that chemists are interested in, and you guys don't really have to worry about too much. Water reacts with water to produce H3O plus and OH minus. So this water forms H2O. In fact, I'll do a different color. H2O to H3O. It has gained an H plus, right? So it has accepted an H plus. H2O, this one turned into OH minus. So this one lost an H plus. It donated. So which one's an acid and which one's a base? Base, acid, accepting versus donating, right? So acid, base. They're the same thing, but one has to be an acid. You can't have one without the other, okay? So in this case, there is the auto-ionization of water. Why all of this is important is it gives us one really important equation and some numbers associated with it. So first of all, in a neutral solution, H3O plus and OH minus equal 10. Their concentration, the auto-ionization happens to 1 times 10 to the 7 times 10 to the negative 7. Doesn't really matter. This is the important equation, okay? H3O times OH minus, the concentrations of those two things in any solution at room temperature is 1 times 10 to the negative 14. The negative 14 is important because that is actually what the pH scale is based on. Is based on going from 1 to 14, all because of that 14 number there. Don't have to ask how we got there. This is the important equation. H3O plus times OH minus yields 1 times 10 to the negative 14, which means these two things are tied together. So if I know that if I have the concentration of OH minus being 5 times 10 to the negative 9th, what is the concentration of H plus? So if I know that the OH minus is 5.0 times 10 to the negative 9, and I know that this is equal to 1 times 10 to the negative 14 molar, by the way, that's molar. What is the concentration of H3O plus? By the way, the little brackets means concentration. Brackets with something inside, these indicate the answer is going to be in molarity, okay? So concentration of H3O plus, and so let's do this math quickly. I'm gonna have to change this to scientific. I think this helps to actually have this here so you can see the calculation. So I'm going to take 1 exp times 10 to the 14th negative, right? And I'm going to divide both sides by 5.0 times 10 to the negative 9th, divide by 5.0 times 10 to the negative 9th. That's what I'm doing. So divided by 5 exp 9th negative equals, oh, this should be, it's annoying. I don't think I know how to change this. Anyway, so 1, 2, 3, 4, 5, 6. Concentration of H3O plus is equal to 2.0 times 10 to the, what was that? 1, 2, 3, 4, 5, 6, right? 5. 6 times 10 to the negative 6. There we go. So that's the concentration of my H3O plus. Again, so you can see how we shift that, okay? All right, good. Let's see. Okay. So this is all equal to Kw, which is about the auto-ionization of water. This is the important equation that you need to know, or you need to have in your brain. If I know, ultimately what this means is if I know the concentration of OH minus, I will always know the concentration of H3O plus. That's the importance of this. If I've got one, I've got the other, okay? All right. And we can rearrange, we're going to talk about rearranging it. So if for a given aqueous solution, if H plus is 1 times 10 to the negative 3, what's the OH minus? Same question for this other one. Okay, so I will let you do those. Those are based on this. Feel free to look through those. I'll finish this before I post it. What are the H plus and OH minus? Again, if I've got one, I've got the other, of a 2.68 molar solution of HBr. All right, so first of all, let's talk about this. I have HBr turns into H plus and Br minus. So if I have 2.86 molar of this, HBr is a strong acid, so I know that it is all going to turn into product, right? So I'm going to have the equal number of H plus and 2.86 molar Br minus. So once those all dissociate, I have 0 of that left. But the idea being, I really just want to focus on this is the concentration of my H plus in solution. So what is the concentration of my H plus? Well, concentration of H plus is actually equal to 2.86 molar. That's it. Problem solved for the H plus. What is the concentration of OH minus? That's a little bit more tricky. So concentration of OH minus is using the equation above. So if we know that concentration of OH minus, I'm just going to rearrange this equation up here, right? The concentration of OH minus is equal to 1.0 times 10 to the negative 14, all divided by the concentration of H plus, which I have, right? So 1 times 10 to the negative 14, all divided by 2.86. So 1 times 10 to the negative 14, 1 times 10 to the negative 14, divided by 2.86. 3.5 times 10 to the negative 15. 3.5 times 10 to the negative 15. There we go. Problem solved. That's it. Molar, capital M. All right. So concentrations of these things are just a matter of figuring out how much H plus, and then you have to use that equation to get OH minus. All right. This next one's a little bit more tricky. Calcium hydroxide. I've got calcium hydroxide with a concentration of 6.02 times 10 to the negative 4 molar. When I put this in solution, I end up with 1 calcium and I end up with 2 hydroxides. So that means that for every one of these, I end up with one of these. So that means the concentration of calcium is 6.02 times 10 to the negative 4 molar. But for every 1 calcium hydroxide, I get 2 hydroxides, which means my concentration is 2 times whatever calcium hydroxide I have. So 6.02 times 10 to the negative 4 molar. So the concentration of OH minus is actually equal to 6.02 exp to the, what is it, 4. Let me just move this over here so you can see what I'm doing. Minus times 2 equals. So 1.2 times 10 to the negative 3 molar. So there's my concentration of OH minus. Plug it into the equation to get H plus. Okay, so yeah, so 1 times 10 to the negative 14 divided by that number should give you your answer for OH minus. Okay, great. Moving on, the last little bit. So the important thing to pull away from there is that equation. This is the important equation to pull out of here. Okay, so that's the important equation to pull out of here. I know one, I know the other. Next, the pH scale. So first of all, whenever you see this P term, lowercase p and then some capital, it just simply means the negative log. So this P term means negative log of whatever's behind it. So px is the equals negative log of x. So pH equals, oh, that's cool. I didn't realize I did that. pH equals negative log of concentration of H plus, or negative log of H3O plus, because they're the same thing. So what do you imagine POH is? Well, POH is equal to the negative log of OH minus. Okay. What do you imagine PI is? Negative log of concentration of I minus, right? So there's all these different terms. The P term is just negative log of whatever's after it, okay? So something that we know is, again, because pH and POH are so connected, like we saw in the last equation, this is an important equation as well. So pH and POH are equal to 14. That was that 14 number again. Those two things are related to one another. So the other version of this is the concentration of H plus times concentration of OH minus, which we just saw above, is 1 times 10 to the negative 14. So you take the negative log of H plus, and so when it's a log thing. But anyway, these are the two equations ultimately that you need to know. Okay, there we go. So those are the two summary equations. These, by the way, this is at 25 degrees Celsius, but we're pretty much always going to use these at 25 degrees Celsius. So simplifying this idea, and we haven't really discussed this much, but anything that is lower has a higher concentration of anything that has a higher concentration of H3O plus, or again, that's just simply H plus, H plus, H plus, is going to be acidic. More H plus in solution means acidic. And the pH is going to be less than 7. Okay. Or OH in solution means greater than 7. So the pH is greater than 7, and pH is the term we use to measure acidity. Okay. And this is the concentration of H plus. So just keep that in mind. So if we go back to our previous solutions and we look, the concentration of H plus is much greater than times 10 to the negative 7. So this is super acidic. Okay. Concentration of H plus is 1 times 10 to the minus 3. This is super acidic. Okay. So we're always looking at the concentration of H plus, though, where that's what we're comparing these things to. So here are different pH values, and we can see the pH of samples. So if we have pure water is a pH of 7, rainwater, coffee, orange juice, wine, stomach acid, all of those are pretty acidic. And we're going to talk about this a little bit more in class, but this is a logarithmic scale. Okay, so what that means is 1 point of pH means that we're multiplying it by 10. Okay, so going from a pH, so rainwater sitting right here and orange juice, right? That is almost 1 point, which doesn't seem like much, but recognize that 1 point means orange juice is 10 times more acidic than rainwater, right? So just recognize that jump is really important. All right. So your blood, by the way, is basic. It has a carbonic acid because of CO2 that's dissolved. So it actually creates a slightly basic solution. And so calculate the pH and pOH of each of the following solutions. So again, we're going to be doing this. I'll do the first one and I'll let you guys do the rest. HCl dissociates into H plus and Cl minus. I don't really care about the Cl minus, but I have 0.200 molar of this and 0.200 molar of that. So let's focus on the H plus. So my concentration of H plus is equal to 0.200 molar. So if I want to do pH, it's equal to the negative log of my concentration of H plus. So again, all I have to do is find that. So I'm going to write the number in, so 0.200, and I'm going to take the log of it, and I want the negative of that log. The pH is 0.69 or 0.70. There's my pH value. Well, so that's pH. What is the pOH? Well, I know pH plus pOH equals 14. So pH, sorry, I'm gonna move pH over. I know pH being 0.70 plus pOH equals 14. pOH equals 14 minus 0.70, which equals 13.3. There we go. There's my pOH. Okay, so just do that for the rest of these and you should be good to go. Okay, perfect. All right, we'll talk about this in class, but this is the basics of acids and bases. Good talk.